What about temperature? We're going to look at the effect of temperature change on reactions which are either exothermic or endothermic. So an exothermic reaction, exo means exit, thermic refers to heat. Heat exiting, it's giving off heat. It is producing heat. Heat is a product, right? So we can think of heat as a product for this. Let me write that out. So an exothermic reaction might be something like A plus B goes to C plus heat. That's not what I, there we go. Plus heat. It's giving off heat. It's producing heat. If we raise the temperature of an exothermic reaction, that's like adding heat. If we increase the heat, it's going to shift. I should have made this an equilibrium. If we, oh, good grief. So if we add heat, which is a product, that's increasing the heat, it'll cause it to shift to the reactant side. If we have an endothermic reaction, then heat is like a reactant. So maybe A plus heat is in equilibrium with B plus C. If I add heat, if I increase the temperature, it's going to shift this way to counteract that, to fight against it. Does that make sense? Think of heat as a reactant or a product. Endothermic means put heat in, so that's a reactant. Exothermic means the heat is exiting, it's being produced, it's a product. And then you can go back to, well, if I add to this, then it shifts the other way. So for an exothermic reaction, heat is a product. If we add heat, it'll shift to the left. If we cool this down, if we take heat away, it will shift to replace that, and it'll shift to the right. An endothermic reaction does the opposite. Here, heat is a reactant. If we add heat, it'll shift to the right. If we remove heat, it'll shift to the left. This is a very interesting reaction. We've been looking at this a couple of times, the N2O4 and the NO2. N2O4 is a colorless gas, and NO2 is a brown gas. And so you can actually put this equilibrium in a sealed container and make the color change by changing the temperature of the container. So this is the same tube. Here we have it in warm water, and it turns brown. We're adding heat. It shifts the equilibrium towards the product, the brown gas. We take that same tube out and put it into an ice bath, and it shifts it to the colorless side. Because here we're sucking heat out of it. We're removing heat. Removing heat, the equilibrium shifts to replace it. Isn't that kind of cool? One of these years, I'm actually going to get one of these and do a demonstration and lecture, and that would be more fun than looking at pictures. So there's the summary. Think of heat as a reactant or a product appropriately, and then ask yourself, well, what if I add product? What if I add reactant? What if I remove it? What happens? Let's look at this equation. We're told that this reaction is exothermic. Is heat a reactant or a product then? It's a product. It's being produced. So I'm actually going to draw that in so I don't forget when I actually look at the question. What's the effect? What's the effect of increasing the temperature? It'll go to the left. I'm adding heat, and it's going to move away from that. So it'll shift left. What if I decrease the temperature? It'll shift the other way, shift to the right. Because if I take heat away, the reaction says, hey, wait a minute. You can't mess with me like that. I wanted that heat there. I'm going to shift over and put some of it back. It's very spiteful. Pardon me? Well, if you write the reaction, if I write the reaction the opposite direction, then it would be the opposite, if that's not too confusing. If I write 2SO3 as the reactant and 2SO2 plus O2 as the product, I write faster than my iPad mini can think. So what I did here is I took this reaction and I switched the reactants and products. But heat is still going to be on the side with the SO3. So we would say that this reaction is endothermic. This is exothermic. Exothermic, endothermic are just directions. Is the heat going in or out? It depends on your point of view. Any other questions?